In this module, we are going to start discussing complex hyperbolic functions. Now, let's see what we have done so far. We defined series of complex numbers, and that using those series, we defined some basic complex valued functions. For example, we defined complex exponential functions, we defined logarithmic functions, we define other trigonometric functions. Now, from here, we have two options. Either we can use series of complex numbers to define further complex valued functions, or we can use previously defined complex valued functions to define new functions. Okay, so in this case of complex hyperbolic functions, we are going to adopt the second strategy, where we are going to use previously defined complex valued functions. So for example, to define complex hyperbolic functions, we are going to use exponential functions. Okay, now the task is how to define. Overall, the strategy is the same. Take the definitions from real analysis and generalize them to complex numbers. Okay, so over here we are going to adopt the same strategy. So in other words, we will be looking for how we define these hyperbolic functions in real analysis. So as you can see on the screen, sine hyperbolic x is equal to e raised to power x minus e raised to power minus x over 2. And similarly, cosine hyperbolic x is defined as e raised to power x plus e raised to power minus x divided by 2. So that's how we define them in real analysis. And of course, if we want to generalize them to the complex variable case, then just replace x with z. Okay, and that's it. That's how we define sine hyperbolic z, where z is a complex number. Okay, which is going to be equal to e raised to power z minus e raised to power minus z divided by 2. So just replace x with z. So that's how we generalize. Okay, and similarly, cosine hyperbolic z is equal to e raised to power z plus e raised to power minus z divided by 2. Of course, if you want a series expression of these hyperbolic functions, then you can always replace e raised to power z and e raised to power minus z with their series expressions, and then you will get a series expression for sine hyperbolic z. And similarly, we can obtain series expression for cosine hyperbolic z. But the definition that you can see on the screen is more than enough to derive the properties of these hyperbolic functions. Okay, now the next question is, of course, there are other hyperbolic functions as well. So how do we define other hyperbolic functions? For example, tangent, cotangent, secant and cosecant hyperbolic z. Okay, so once again, if we have defined sine hyperbolic z and cosine hyperbolic z, then we can easily define the other trigonometric functions. So for example, we can define tan hyperbolic z to be equal to sine hyperbolic z over cosine hyperbolic z. And if you want to calculate things, then you want a definition of tan hyperbolic z which involves exponential powers. So easily we can see that this is going to be equal to e raised to power z, since sine hyperbolic z is equal to e raised to power z minus e raised to power minus z divided by 2. Okay, so this whole divided by 2. And similarly, cosine hyperbolic z is going to be equal to e raised to power z plus e raised to power minus z whole divided by 2. And then of course this 2 and 2 will be cancelled out, and what you will get at the end is e raised to power z minus e raised to power minus z over e raised to power z plus e raised to power minus z. So that's the definition of tan hyperbolic z that involves the exponential function. And of course, if you want a series expression, you know, in this case it will involve some non-trivial steps, but eventually using this definition you can easily get the series expression for tan hyperbolic z. I'm leaving this as an interesting exercise for you. And similarly, cotangent hyperbolic z is going to be equal to cosine hyperbolic z divided by sine hyperbolic z, and of course very trivially we can easily write it down as e raised to power z minus e raised to power minus z over e raised to power z plus e raised to power minus z, using the same strategy. And similarly, moving on to other hyperbolic functions, secant hyperbolic z is 1 over cosine hyperbolic z. Of course, this is going to be equal to 2 over e raised to power z plus e raised to power minus z. Okay, so just invert the value of cosine hyperbolic z, and similarly if you invert the value of sine hyperbolic z, you'll get the value of cosecant hyperbolic z. So this is going to be equal to 2 over e raised to power z minus e raised to power minus z. So that's how we define complex hyperbolic functions. Now moving on to the next property, next important property of a function, which is the derivative. And now we want to talk about the derivatives of hyperbolic functions. Okay. Now, there is one important remark here. If you want to consider the derivatives, then we know that we only know calculating the derivatives only for functions. Okay, so in other words, not multi-valued functions, but just for functions. So we need to make sure that the derivative of the function is basically a function and not a multi-valued function. Okay, so over here, if we are writing down the derivative of cosine hyperbolic z, then it means that we are considering the principal branch, or the branch which is basically a function by definition and not a multi-valued function. So basically, when we are writing down these derivatives, it means that we are writing down the derivatives of the principal branch of those functions, or just take one branch of these functions and then we can write down this expression. So in other words, there is some condition on the domain, there is some condition on the z for this derivative to work. Okay, so that condition on the z will make sure that you are restricted to one particular branch of this function. Okay. And similarly, on the screen you can see other derivative formulas. D by dz of sine hyperbolic z is cosine hyperbolic z. Derivative of tangent hyperbolic z is equal to secant hyperbolic square z, and derivative of cotangent hyperbolic z is equal to minus cosecant hyperbolic square z, and the derivative of secant hyperbolic z is minus secant hyperbolic z tangent hyperbolic z, and the derivative of cosecant hyperbolic z is equal to minus cosecant hyperbolic z cotangent hyperbolic z. So that's how we calculate the derivatives. Of course, the question would be how do we calculate, or how do we derive these formulas? So the derivation of these formulas is relatively simple, because the definition of these functions involve exponential function, and exponential function has a very simple derivative. So let me calculate, or let me prove the first formula. Okay, so let's focus on this thing. Okay, so we know that how do we define cosine hyperbolic z? So cosine hyperbolic z is defined as e raised to power z plus e raised to power minus z divided by 2. And using the properties of the derivative that we have discussed so far, this is going to be equal to e raised to power z. Using the chain rule in the second part, okay, so let me highlight this thing. So in the second part, we are using the chain rule. So minus e raised to power minus z. Okay, so chain rule means we take the derivative of e raised to power minus z and then the derivative of minus z, which is minus 1. So divided by 2. So 1 by 2 is a constant, so there will be no change. And by definition, this is exactly sine hyperbolic z. And as you can see that we obtained this formula in a very simple way, and similarly we can obtain the other formulas once again using the exponential the definition of these hyperbolic functions that involves the exponential function. Okay. Now there are two important identities which are often useful in our calculations. So one of the identity is cosine hyperbolic x plus iota y is equal to cosine y cosine hyperbolic x iota plus iota sine hyperbolic x sine y. Okay, and similarly sine hyperbolic x plus iota y is going to be equal to sine hyperbolic x cosine y plus iota cosine hyperbolic x sine y. Okay, now the point is how to prove these identities. Okay, now let's focus on the first identity, and of course the proof of the second identity is going to be very similar. Okay, now we know that what is cosine hyperbolic z. Once again, by definition, this is going to be equal to, okay, so if z is x plus iota y, so let's just replace z with x plus iota y. So this is going to be equal to e raised to power x plus iota y plus e raised to power minus x minus iota y divided by 2. And once again, we are using the following definition of cosine hyperbolic z. So this is going to be equal to e raised to power z plus e raised to power minus z divided by 2. So we are using this definition. Now we can expand this in the following form: e raised to power x and e raised to power iota y. Okay, and we know that how to deal with e raised to power iota y. Okay, so minus x e raised to power minus iota y divided by 2. So this becomes e raised to power, let me write down 1 over 2 over here, and e raised to power x, and then we have cosine y plus iota sine y. Okay, and plus e raised to power minus x, okay, and cosine y minus, because there is a minus iota y, so minus iota sine y. Okay, now you have to be careful, so carefully adding the terms in the following way. Okay, so e raised to power x cosine y, e raised to power minus x cosine y. So let me write down these terms separately. So e raised to power x plus e raised to power minus x, and in these two terms cosine y is common. Okay, and now let's consider the second terms, so these two terms. Okay, so once again plus 1 by 2, so in fact there is iota which is common, so iota by 2, and sine y is also common, so let me write down sine y over here, and then e raised to power x, e raised to power x, and e raised to power minus x, but with a minus sign between them, minus e raised to power minus x divided by 2, so 2 is already there. Okay, now what do we get? So we get the following expression, 1 by 2. So let me replace 1 by 2 e raised to power x plus e raised to power minus x with cosine hyperbolic x. So we get cosine hyperbolic x cosine y, and in the next term we have iota, and e raised to power x minus e raised to power minus x divided by 2 is basically sine hyperbolic x. Okay, so and then sine y will remain the same, so sine y, and as you can see that this is exactly this identity, so we can say that cosine hyperbolic x plus iota y is equal to this expression. So since it is true for each and every complex number, so that's why we call it identity. So similarly we can prove the next identity, okay, that involves sine hyperbolic x plus iota y, and obviously as you can guess that we are going to use the definition of sine hyperbolic x plus iota y to be equal to e raised to power x plus iota y minus e raised to power minus x minus iota y divided by 2, and simplifying the expression we can easily get the right hand side of this identity. Now moving on to other properties of cosine hyperbolic and sine hyperbolic functions, and most importantly these identities are important because they relate the hyperbolic functions with the trigonometric functions. Okay, so for example the first identity relates if you replace z with iota z, and cosine hyperbolic iota z is basically equal to cosine z. Okay, so it relates, and this is a kind of bridge between the hyperbolic functions and the trigonometric functions, and we can easily use this bridge to derive properties, other properties of hyperbolic functions using the properties of trigonometric functions. And moving on to the next property, the next property once again relates the sine hyperbolic iota z is equal to iota sine z. So relates hyperbolic function with the trigonometric function. Once again the next two properties relates the hyperbolic functions with the trigonometric functions. Okay, so the proofs of these properties are extremely simple. So once again using the exponential, the definition of these hyperbolic functions that involves the exponential function. So of course cosine hyperbolic iota z. Okay, so if it is cosine hyperbolic z, then this is going to be equal to e raised to power z plus e raised to power minus z divided by 2, and if it is cosine hyperbolic iota z, then it is going to be equal to e raised to power iota z. So just replace z with iota z. Okay, so e raised to power iota z plus e raised to power minus iota z divided by 2, and from the definition of cosine z, as we have discussed in our previous modules, is going to be exactly equal to cosine z. Okay, and similarly the next property, sine hyperbolic iota z is going to be equal to iota sine z. Okay, so basically once again replacing z with iota z in the definition of sine hyperbolic function, okay, minus iota z divided by 2. Now we know that from our discussion of trigonometric function that this is going to be equal to sine, but only if there is 2 iota in the denominator. So what we do, we multiply and divide with iota, okay, iota z divided by 2 iota. Now this expression is basically sine z, and here we have iota, so this is equal to iota sine z, so that's this identity. And similarly we can prove the other two identities. So that's how we prove these simple very simple but very powerful relations between the hyperbolic functions and the trigonometric functions. Okay, so using these relations we can prove some very powerful identities which are very famous and very useful in our calculations. Okay, so our first powerful and very famous identity is cosine hyperbolic square z minus sine hyperbolic square z is equal to 1. Okay, so how to prove this identity? Now we have proved that cosine hyperbolic iota z is equal to cosine z. Okay, so which definitely implies, so if we just replace z with iota z, so what do we get? So this implies cosine hyperbolic iota square z is equal to cosine iota z, and we know that cosine hyperbolic, so iota square is -1 and cosine hyperbolic minus z is equal to cosine hyperbolic z, so that's equal to, so cosine hyperbolic z is equal to cosine iota z. So we have derived this relation. And similarly for sine we can replace iota with, if replace z with iota z. Okay, so replace z with iota z, what do we get? So sine iota square z is equal to iota sine iota z. Okay, so we are just replacing this in this property. Okay, so now what is sine iota square? So sine minus, okay, so sine minus z, okay, and which is going to be equal to iota sine iota z. And we know that sine minus z is equal to minus sine z, so this implies minus sine z is going to be equal to iota sine iota z, and multiplying both sides with the -1 we easily get this identity. Okay, now using this first property and the second property, we can see that on right hand side we have cosine iota z and sine iota z. So let's calculate this cosine hyperbolic square z minus sine hyperbolic square z. Okay, so this is going to be equal to cosine square iota z and minus iota sine iota z, and which is going to be equal to cosine square iota z, and this is iota square, so it becomes minus, and this minus is basically this minus becomes +1, and so what we get? Plus sine square iota z. And we know that for trigonometric functions sine square z plus cosine square z is equal to 1, so this is equal to 1. Now moving on to the next property. Now using cosine hyperbolic z is equal to cosine iota z, we can easily prove this property. This will help us in expanding this angle. Okay, so cosine hyperbolic z1 plus z2. Okay, so if we can expand this thing, then we can easily discuss, so for example, what is going to be cosine hyperbolic z1 plus pi by 2, for example, and similarly what is going to be cosine hyperbolic z1 plus pi, and similarly other properties can be obtained. And last but not least, we have the following identity that you can see on the screen, and using this property that we proved, very simple but very effective property, and of course this identity involves the relationship between hyperbolic and trigonometric function. So that's why using the properties of trigonometric functions we can easily prove this identity. So in this module, we introduced what are complex hyperbolic functions, and then we derived different properties of these hyperbolic functions.